Okay, hey everybody. This is part 5 of lecture 6, and for part 4 I had the video up, and then it quadrupled the size of the file, the movie file, and quadrupled the time of the upload. So no video of Hank this time. Before I start on kind of the last technical piece, I want to reinforce what I just posted to Piazza. There was a bug in this slide, and I actually presented this slide in part 1 of the lecture, and now I'm going back to it, where this was correct. It said 1E was going to be due on February 6th, but down here it was incorrect. It had 1E over in the February 7th column. And, like I said in my Piazza post, when I make mistakes, I like to then give you guys the more generous timeline. But we're actually pretty far away from that February 6th, 7th date, and nothing got up on Canvas or the PDF. And this slide was, probably most people would have seen that date. And moreover, that February 6th date works better because I would like it to be that if folks aren't able to get finished, then I can work with them on February 7th and get them to success. So I am going to stick with February 6th, and if there's a concern out there, please let me know. So good. So now we're going to talk about the view transform. And so we've already, said this a couple times, or I've said this a couple times. There's three matrices. One is the camera transform that takes you from world space to camera space. The second is the view transform. That's what we're talking about right now, that takes you from camera space to image space. And the third is the device space transform. And we've done these out of order because we already did the device space transform in an earlier video, and we just did the camera transform. So you would be doing camera transform, view transform, and then device space transform, even though that's not the order I lectured in. So let's talk about the view transform. So first, for the slides that we're looking at, I'm going to look at a 2D cross-section of the three-dimensional space. So on the left, we've got the camera. We're looking down the negative z direction, which of course, we've defined our w basis vector to be facing away from that negative z. We've got our near plane and our far plane. We have our so-called view frustum because the tip of the pyramid is being cut off, as well as everything beyond the far plane is being cut off. And so this picture here is looking at a cross section that is keeping V, so it would be flat. If you look at the plane that connects up the V and W and goes out, that cross section is this picture right here. So there V goes up, there V goes up, there V goes down, and V is going down there, and there W is going to the left, and there W is going to the left. And of course, then here is a cross section of our view frustum. So we're not looking at any changes in U. This would be, for example, in fact, not just for example, specifically the U equals 0 plane. And it's going to be easier for us to think about some of these things if we think about a two-dimensional cross section of the view frustum, because I want to look at some points and how the view transform affects those points. And so now, we can see this same near plane, so it's n units away, and the far plane is f units away, and the camera angle is alpha. And these are the three things that actually you need to specify the view transform, because everything else is fixed. The camera position is already known, the view direction is already known. These are the last three things that need to get baked in, and they happen during the view transform. So, what's going to happen is we're going to have data that's going to be sitting inside this view frustum. And again, I think we'll see an example where it's a square, and then the square is going to get stretched out. And so, oops, darn it, I got this fixed in most places, but not here. And so what we're going to see is that this space, this frustum, is going to get mapped to this square. And so the top, this angled part is going to become the top of this box. This bottom angled part is going to become the bottom of the box. The left near plane is going to be the left of this box. And the right far plane is going to be the right of the box. And so this will be v equals minus 1, the top will be v equals plus 1, the left will be w equals plus 1, and the right will be w equals minus 1. And so, this is doing something that's not just rotations or scales. It's actually doing something more complex because it's actually adding perspective. And so, things that are this right here, this near plane, which is somewhat narrow, is going to occupy the same height as the far plane, which is much wider than the near plane. And so an object like this square will get transformed so that we see it with perspective. So I'm not going to derive the view transform. I don't think it's a good use of class time, but there is a very nice write-up by Ken Joy on his graphics notes, and I encourage you to look at that if you want to understand how the matrix is derived. Instead, we're just going to look at what the matrix is. And so again, it has 3 input parameters: an angle, alpha, a near plane, and a far plane, and it transforms the view frustum to the image space cube. And so this view frustum, again, is bounded by the viewing pyramid and the planes z equals minus n and z equals minus f. And here's our image space cube, which is going to be the output. And then here's the matrix itself. And so this is cotangent. Cotangent is 1 over the tangent. This is alpha over 2. By the way, I will always be specifying angles in radians, and also the C math function, sine, cosine, tangent, etc., also work in radians. So as you're getting these angles, you'll probably just want to keep in mind they're in radians, and as you print them and so on, you're getting radians and not degrees. And so you've got for the x and y portion of the matrix cotangent of alpha over 2, and then you've got these other terms for the second row column, f plus n divided by f minus n. For the third row, second column, 2fn divided by f minus n. And you can see here, this is something that's unusual, is everything we've seen up until now has a 1 here and zeros there, and now we've got a minus 1 in the second row, third column, and a 0 in the third row, third column. So this is the view transform. This is our third matrix. And again, you can define this matrix entirely from the alpha, near, and far. So let's do an example. And so for our example, we're going to look at an alpha of, and of course I've said it's in radians, and here this is in degrees, but whatever, in the program it's going to be in radians. We like to think in degrees. So an alpha of 90 degrees, a near plane of 5, and a far plane of 10. And so here I've annotated the picture showing that the angle is 90 degrees. Of course, this angle in reality is much less than 90 degrees, but that's okay. Assume that it actually is 90 degrees, a near plane of 5 and a far plane of 10. Are these really 5 and 10 units away? I don't know. The near looks to me like the far is more than twice as far away as the near, but again, just assume that these numbers are correct, and the graph just is shifted a little bit. So if we do this example, then we get this matrix right here. So the cotangent of alpha, cotangent of 45 degrees is 1. And then f plus n is 15, divided by f minus n is 5, so that looks like a 3. 2 times fn is 2 times 5 times 10, that sounds like 100, over 10 minus 5, that sounds like 5, so this would be 20. So I think this should be 1, 1, 3, 20, minus 1, and that's what we got. Okay, so that would be the view transform for this set of camera parameters for the angle and near and far plane. So let's multiply some points. So if we multiply the point 0, 7, minus 6, 1, then we put it right here, 0, 7, minus 6, 1, and then we would take this row, 0, 7, minus 6, 1 times this column, that would be 0. This row times that column would be 7. So the first coordinate would be 0, the second coordinate would be 7. We would get that for the row times this column, it would be minus 18 plus 20, so it would be 2, and the last one would be 6. So the output here would be 0, 7, 2, 6. And I'm not going to do the other one. It looks like the other one was 0, 7, minus 4, 8. And then, as we discussed in one of the earlier videos, these points are getting pulled off the w equals 1 plane, and when that happens we have to project them back, and the way we project them back is we divide by the w value of the output. And so now I'm taking each of these three and dividing by 6 for this one, and getting 0, 1.16, and 0.33. Of course, this is approximate, it actually be 1.666. And then here I'm dividing by its w value, which is 8, and getting 0, 0.875, and minus a half. And so I want to say, there's a pitfall that I see every year where people forget to divide by w, and also a pitfall where people are sending in three-dimensional points because the matrix calculations are taking four-dimensional points as input and creating four-dimensional points as output. So make sure that you're declaring 4 doubles and that you're assigning the last point value to be 1 in the input, and then again dividing by w in the output. And so then if we look at these points, then this says, well, we're looking at u is 0, so this just kind of drops out. Or whatever the values were, it wouldn't show up in this projection. And then the v values are 7, and so this one, if we look at sorry, I should be looking at this one. These are the input points. So these are the input points we should be looking at when we plot it on this picture. These are the output points, and so we should be thinking about these with respect to the image cube. And so this one says that we should be going 7 units up and 6 units, 7 units up and 6 units over. And this is not quite 90 degrees, but even if it was, 90 degrees is in terms of what's above the v equals 0 line, that would be 45 degrees to the line y equals x, and y equals x. And so 7 is outside. That means it would be outside the view frustum. And that's what we see here, is that it's too large, that the amount that this angle is expanding is not wide enough to capture something that's that high when we're only going 6 units out. If it was at 0, 6, minus 6, then it'd be right on the line. In this case, now when it's 0, 7, it'd be something like minus 8. So the first one was actually, I think I said it wrong, would be past the near plane, but up here. And with the other one, it's getting the same height, but now it's moving inside the view frustum. And we can see this is showing up as a valid value inside the image cube, while this one does not show up inside the image cube. So let's look at some more examples, some more points. We're looking at 0, 7. All these are 0, 7, minus 4, minus 5, minus 6, minus 8, minus 10, and then what their outputs are with respect to the image cube. And I have these plotted, so let's just do this going back to this picture we looked at before where we have things in camera space, and then we look at them in image space. And so here are points in camera space. So this would be 0, 7, minus 4, 0, 7, minus 5, so right on the near plane, 0, 7, minus 6, so still not inside, 0, 7, minus 8, 0, 7, minus 10, so right on the far plane, and 0, 7, minus 11. And so for minus 11, this gets mapped to 0.63 minus 1.18, so it gets mapped to a value that's less than w equals minus 1, and so it's past the far plane. And this is exactly why in Project 1D we treated z equals minus 1 as the minimum value we want to put in the z buffer, because anything that is mapped to a value that's past the far plane is going to get a w value of smaller than minus 1. The point that was on the far plane shows up in the image cube. This point that was inside the view frustum shows up inside the image cube. That's good. This point that was outside of the view frustum shows up as being outside the image cube because its y value is too large. Its v value is too large, and that makes perfect sense based on this picture. And then again, the one that's on the near plane gets a w value that's consistent with the near plane, but then its v value is too big to be on the image cube, which again looks correct. And then this one right here ends up being in front of the near plane and also having too large of a v value. And it's interesting, there's a very non-linear relationship. Here it says z, this should say w. although I'll put Z because we call it the Z buffer algorithm, but this is labeled as the W space. And so what we're seeing is that one step here from -4 to -5 takes us a full step in W here, but then one more step only takes us 2/3 of a step, and then here we've taken 2 steps and it only takes us less than a step, but here we take a step and it's only taking us like 1/5 of a step. And so what's happening is things that are closer to the near plane take up more resolution in the front. They get mapped to a bigger space. So things that are packed together here, I'm drawing that small, get a bigger part of the image cube. And that's just how the math works. There's actually corrections that people do for that. They call it W buffering. Okay, so here's our putting it all together slide, and we looked at this once before. When we get a camera C, we're going to calculate the camera frame. Once we have the camera frame, we can calculate the camera transform. We can also calculate the view transform and the device transform. We take these 3 matrices and compose them into one matrix we call M. And then for each world space triangle, we multiply each vertex of that triangle by M. And then at the end, we rasterize it and we apply a Z-buffer algorithm. And I should remove this as well because that Phong shading is actually going to be project 1F. And so I got that fixed in one slide, but not another. So that's the last thing for us to do is we're going to do shading. So good, so this kind of ends the technical piece, and the rest will be an orientation to project 1E. So I hope this all makes sense, and if not, send me emails and we can post comments on the videos to clarify any mistakes I've made or just make things that weren't very clear clearer. So I hope this was useful. This is pretty math heavy. These are math heavy slides, but I'm hoping that this is actually a really good set of videos to do on YouTube because it lets you really understand how to use these matrices and lets you kind of just look at them and understand them as you're implementing them in your code. Okay, one more video to come, which is the Project 1E orientation. Bye, guys.